Hello everyone, in this lecture we're going to be talking about different types of titration curves and important points you want to make sure you understand and be able to retrieve a lot of information from those points. I'm going to be talking about the strong acid, strong base, weak acid, strong base, a strong acid, weak base, and then I'll talk about the diprotic acid and the base as well. So before we jump into the titration curves and look at those, let's understand some of these important points. I'll talk about equivalence point. Equivalence point, some books will have a symbol as an EP there. It just means you have neutralized all the acid or all the base by the opposite party. Another way of saying your moles of base is going to be equal to the moles of acid, and you can say that otherwise as well. The moles of acid equal to the moles of base, depending on what you're really titrating. And once you reach the equivalence point, you're going to have a particular pH of the solution depending on what type of base and acid is being titrated. So we'll get to that in a minute. And then I do want to talk about something called an endpoint. Endpoint is usually used when you actually do the titration in the lab by using some sort of indicator where it's going to be changing the color. So usually the end point is going to be a little bit over the equivalence point. So once you have the equivalence point reached, after reaching the equivalence point, you may need an extra drop of an acid or a base to increase the pH or decrease the pH depending on which way you're going, and that's when you're going to see the change in color, and that's where your endpoint is going to be reached. And that's going to be completely okay to just rely on the endpoint as your equivalence point, even though they are not the same. That's because after adding maybe a drop after reaching the equivalence point in order to get to the endpoint, the calculations are not going to be changing significantly, because how are you really going to account for a drop of acid or base after reaching the equivalence point? So their calculations will still be the same, but keep in mind your endpoint is more like when does the color change, and your equivalence point is when the base is actually equal to the moles of acid. The other thing you want to know is the half equivalence point. Obviously, as the name specifies, you're only going to be neutralizing half of your original acid or base. And other important thing you want to make sure you know, if I'm titrating suppose an acid, then at half equivalence point, the concentration of your acid and the concentration of your conjugate base is going to be the same. And then I can say that otherwise as well. If I'm titrating the base, then the concentration of your base and the concentration of your conjugate acid is going to be the same. In addition to that, the other important point you want to make sure you know is at half equivalence point, if you're titrating a weak acid, that really applies when you have a weak acid or a weak base, the pH is going to be equal to the pKa, and then the pOH is going to be equal to the pKb. So those are two important things that you want to make sure you know, and that's obviously coming from the Henderson-Hasselbalch equation, because you have your conjugate acid and base to be equal in amount, and the same can be said about the acid and the conjugate base to be equal in amount. The buffer region is usually going to be 1 unit up and down from the pKa. So I would say pKa if it is 4. So I'm just supposing like you have a pKa of 4, then your buffer region is going to be from 3.0 to 5.0. So that's always going to be the typical case. You have a buffer region from 1 unit up and down from your original pKa value for a particular weak acid or a weak base. Okay, let's talk about the titration now. Suppose I'm titrating here a strong acid, strong base, and I also have the graph for the weak acid and strong base. So let's focus on the graph that's dealing with the strong acid and strong base. So we're looking at this yellow graph on this figure there. So we have the pH on the x-axis, and then we got the volume of this strong base. That's going to be the LiOH I'm dealing with. That's being added here. when you reach the equivalence point, at equivalence point, your pH is always going to be 7.0. Now, that's going to be true anytime you're dealing with a titration of strong acid and strong base. And how do you really figure out the pH when you are looking at the graph? So when I'm looking at the graph, I'm going to be looking at the midpoint of your jump. So when I'm looking at this yellow line, the yellow kind of started jumping right here, and then it had kind of embedded in the green line as well. But just kind of think it's right there. So I'm looking at the midpoint between those, between the jump there. So the midpoint is going to be somewhere around 7 there. So that's what your pH going to be at the equivalence point. Now, when I'm titrating a weak acid with a strong base at equivalence point, I'll change the color there. At equivalence point, your pH is going to be a little bit over 7. So always think of this way. Whichever is going to be strong is going to be winning in terms of finding the pH at equivalence point. Like in the previous case, both of those were strong, so no one wins, so that's why your pH stays neutral at equivalence point. But now I'm doing a weak acid and strong base, so you have a strong base, it's going to win over the weak acid, and as a result, at equivalence point, your pH is going to be a little bit basic, which is going to be a little bit over 7.0. Now, how much over it's going to be, that really has to do with the calculations or by looking at the graph, but just keep in mind, generally, it's going to be a little bit over 7. Now, how do I figure out the pH on this graph here? So when I'm looking at this green graph, my jump kind of starts right here, and then the jump is kind of ending right there, and that's when it kind of becomes a flat line. And when I'm looking at the midpoint of those two, it's going to be, I would say, somewhere down there. So that's going to be your pH at the equivalence point, which is about 9. So that's what we're really looking at there. Now, in addition to that, also be able to figure out how much volume you really use to reach the equivalence point. And in both of those cases, we're looking at 25 milliliters that's needed to reach the equivalence point. Now, what's happening at half equivalence point? So at half equivalence point, I'm going to be looking at when you are adding half of the base. So to reach equivalence point, we need 25 milliliters. All right, so I'm going to write that down here. So 25 milliliters in both of those cases. To reach half equivalence point, I would need 12.5 milliliters. So I'm going to go down here and make a mark where it's going to be 12.5. So it's going to be somewhere down there. And then I can probably draw a line going up here. Okay, and it's not that important. You don't really retrieve important information at half equivalence point when you're dealing with strong acid, strong base, but you do get a big chunk of information when you're dealing with the weak acid and strong base, and even a weak base and strong acid. So then when I'm looking at my, suppose the weak acid and strong base, wherever it meets right there, I'm going to draw a horizontal line there and see where it meets on the pH. So remember, at half equivalence point, your HA concentration is going to be equal to the A minus concentration. And when I'm looking at my Henderson-Hasselbalch equation, so which is going to be pH equals pKa plus log of A minus over HA. So since your A minus and HA concentration is going to be the same, this kind of goes away because that's going to be 1 and log 1 is going to be 0. And as a result, your pH is going to be equal to the pKa. So at half equivalence point, from the graph, you can figure out what's going to be the pKa. So at this point right there, that's going to be the pKa of that particular weak acid, which comes out to be, if I roughly look at here, it's going to be somewhere around 4.5, I would say. So then if your pKa here is about 4.5, then what's going to be the range of your buffer solution? Well, I'm looking at anywhere between 3.5 to 5.5. So this, if I draw another line here, So starting maybe right here and then going all the way up here. So it seems like that's going to be your buffer region there, because you want to make sure you can go 1 unit above and 1 unit down from the pKa values in order to have the buffer solution. So that's why this graph is kind of increasing slowly when you are adding the LiOH. But when I'm looking at the strong acid, there's really not that kind of line there. It's just like it increases very, very slow, and then all of a sudden there is no buffer there. There is no buffer region there, and then it loses that pH into the neutral side and then onto the basic side. But you do have this buffer region there, and then you want to make sure you are able to identify where the buffer region gonna be when you're dealing with these weak acids or weak bases. Okay, let's look at a titration of a weak base with a strong acid. So I do have a titration curve here for a strong acid or a strong base. It's just like you going opposite, like you're starting out with a base and then you start adding the acid into it. And then if you're starting out with a base, you will have a very high pH, and that's what exactly you have right there. Let me change the color there. So that's exactly what you have there. And then as you start adding the acid, your pH is going to start decreasing. And as soon as you lose all of the base, it's going to have a sharp jump. So when I'm looking at this sharp jump, this kind of overlaps onto this blue line. So your jump is kind of starting right here, and then it's kind of going all the way to, I would say, right there. Then what's going to be the midpoint of that? Well, it's going to be somewhere right there. So it's still the pH of your strong base and strong acid is still going to be the 7. But I'm going to be focusing more on to the weak base and the strong acid here. That's going to be this blue line here. And then on this blue line, let's see, I'm starting the pH at about 11, which makes sense because you're going to have a weaker base, so the pH of that weaker base is going to be a little bit less than 14. It's not going to be close to 14. Let me change the color there. Okay, so then as you're moving along, you can see where your jump is starting, or another way of saying where your equivalence point going to be. I'm starting right here, and your graph is kind of leveling off right there. So your equivalence point is going to be right in the middle there that this picture has shown here. That's about, I would say 5.5. That's where your equivalence point is. And how much volume did I need to reach the equivalence point? I'm looking at about 50 milliliters. So I'll need 50 milliliters to reach equivalence point. And the pH at equivalence point, since I'm dealing with a strong acid and weak base, it's going to be less than 7. So that's one thing you want to make sure you understand. The pH is going to be less than 7 because it's a strong acid and weak base. And what exactly that's really going to be, we can look at that graph. And in this particular case, it seems like that equivalence point, the pH is about 5.5. Now, what happens at half equivalence point? Now, at half equivalence point, we will be adding only 25 milliliters because you're only going to be neutralizing half of the base there using that strong acid. So at 25, let's draw a line there. So at 25, I'm going to be right here. I'm going to draw a horizontal line there. So then that's what I'm looking at. So it's about a pH of 9. So at half equivalence point, the base and its conjugate acid, so I'll write down BH plus, are going to be equal to one another. And if I want to go ahead and write down in terms of your POH equation for the Henderson-Hasselbalch, so it's going to be POH equals pKb plus log of your conjugate acid, which is going to be BH plus, divided by the base. Now I know the base and the conjugate acid are the same at half equivalence point, so this is going to become, their ratio is going to be 1, so log 1 is going to be 0, so that means your POH is going to be equal to the pKb of that particular acid. Now what's the POH at this particular point? Well, I know the pH here is 9, so the pOH is going to be 14 minus 9 roughly, so that's going to be giving you 5. So that means the pKb of this particular base is going to be 5. So that's how you're going to be retrieving a good chunk of information from these graphs. Okay, what if you have a diprotic acid? Okay, and even if you have a triprotic acid, it's going to be similar, but I'll do an example of diprotic acid, and the triprotic acid is just going to be in a similar, just in another proton in there. So if you see a diprotic acid, you will have two jumps in there. I can look at the first jump to be right here, okay, and then it will be needing how much, so that's going to be called your first equivalence point. So at first equivalence point, I'm going to be looking at the 10 milliliters of the volume and what's going to be the pH at first equivalence point. Now you can't really tell whether it's going to be less than a particular number because that's really dependent on what the pKa's are. So by looking at the graph, your biggest jump and the midpoint of that sharp jump there is going to be around 4. So the first equivalence point, your pH is going to be about 4, let's say 4.0 roughly. And then what's going to be at the half equivalence point? At half equivalence point, we're going to be neutralizing only half of that diprotic acid, so I'm going to be having only 5 milliliters in there. And then at 5 milliliters, so I'm going to roughly draw this line right there and draw a line across where the conjugate base and the acid is going to be the same. So as a result, the pH is going to be equal to 2.1, I would say. So that means this particular pH is going to be equal to the pKa1. So it's going to be about 2.1. Remember, we're dealing with diprotic acid, so you're going to have two protons in there, and as a result, you're going to have two pKa values. You're going to have pKa1, and then you're going to have a pKa2. So to figure out pKa1, you focus on your first equivalence point. And then if you're trying to figure out the pKa2, you look for your second equivalence point. And then if it's a triprotic acid, then you would have another equivalence point or the third equivalence point, and you can look at the third equivalence point to find the pKa3 in that particular case. So let's look at what's going on with the second equivalence point. So your second equivalence point, I would say your jump kind of starts right here, and it goes all the way up to here. So the midpoint is going to be somewhere right there. So I'll draw a line here. So that's how much volume it's going to be needing to reach the equivalence point. Well, it's got 20 milliliters. So remember, that has to be doubled from your first equivalence point. Because if you lose the first proton after 10 milliliters, the second proton must be lost by adding another 10 milliliters. So the total volume is going to be 20 milliliters there. And then where is going to be, well, let's see, what's going to be the pH at the second equivalence point in this particular case? We're looking at a little bit over 9, so I would say maybe 9.1 here. And then what else is going on? What's going to be your second half equivalence point? So this is a little bit important to understand where it's the second half equivalence point going to be. It's not going to be the half of 20, because remember, half of the 20 is 10, and that's where your first equivalence point was. Your second half equivalence point is going to be in between the first and second equivalence point. So another way of saying, add about 15 milliliters. Because by 15 milliliters, you would lose half of the second proton. So it's going to be right here. So I'm looking at pH of about 6.5. So at second half equivalence point, which will be needing 15 milliliters of your base here, your pH is going to be about 6.5. And what does that pH going to be equal to? Well, since you're losing the second proton, it's going to be equal to the pKa2. So this is how you're going to be figuring out what the pKa1, pKa2 going to be. And obviously you can look at the buffer regions as well. Your buffer region for the pKa1 is going to be 1 unit up and down from the 2.1, and the buffer region for the second loss of proton is going to be 1 unit up and down from 6.5. And similarly, if you have a triprotic acid, then you would have another equivalence point, and using that equivalence point, you can figure out the information of the pKa3. So hopefully this was helpful. If you have any questions, feel free to leave any comments in the section below.